Okay. Hello everyone in this recording for the conference. So OpenAPI specification is great because it defines a standard for APIs. And it would be great to have a tool that can directly create workflows from these specifications files, right? So hello everyone, I'm Gutierrez Diez, Principal Software Engineer at FactSet, where I lead a distributed team of fantastic engineering. And I'm based in Frankfurt, Germany, but I come from Spain, so you can say last summer was great. FactSet is a Standard & Poor's 500 company with offices around the world. Our teams are distributed and we let engineers decide where they want to work, remote, hybrid, or in office. As an API-first company, FactSet defines standards and guidelines around API implementations and processes that teams are enforced to follow. In today's prep, I'm going to show how FactSet is able to create workflows directly from OpenAPI specs in an automated manner and how these workflows are then orchestrated within applications and services. I am also going to touch on some Amazon Web Services used in our backend and some cool and not so cool things about them. Well, the FactSet API was launched some years ago in order to standardize the creation and maintenance of the APIs. And the API program guides teams and provides a specific tooling when working with APIs. Teams are enforced to follow conventions and best practices when creating APIs, and several committees are in charge of helping and guide them and provide support when needed. Some different tools are made available to calculate the score of an API, so APIs with low score are not allowed to be published and used. API quality score takes into consideration the design of the API, including request response specification, its versioning system, its usage of health checks, monitoring tools, and many other things. In this conference, probably everybody knows what the OpenAPI spec is, but just a brief reminder. It is a document that specifies a standard to follow for the different endpoints of an API, including paths, parameter responses, headers, errors, etc. OpenAPI specs can be automatically generated from the source code or can be created manually. In FactSet, we recommend definition-first approach, so APIs are defined before the proper implementation starts, and the OpenAPI spec document is created before that. This approach has the benefit that discussions around the API interface can happen at the beginning of their design, so it is cheaper to consider things than trying to change them once they are implemented and starting to be tested. OpenAPI specs are used in FactSet to leverage and automate different tools and products. For example, the developer portal, the enterprise SDKs, or the workflow manager. Within FactSet API programs, several initiatives like this one have been started. For example, the developer portal is available in the FactSet.com landing page. It's the showroom of FactSet client-facing APIs, and it uses OpenAPI spec to describe and list the usage of the different APIs available. It offers documentation, tutorials, example cases, tryouts, and many more information about the APIs. The SDKs are available on the FactSet GitHub page, and they can be used to execute and use different inputs of our APIs in different programming languages, like Python, .NET, Java, or TypeScript. The SDKs are using OpenAPI spec to auto-generate a big portion of their code for all the new APIs. And finally, for example, the workflow manager, which is my tool, the tool that my team is responsible for, and I'm going to spend more time talking to them. This tool allows creation and orchestration of workflows by combining different user and system tasks, and it uses OpenAPI spec to import endpoints and as tasks and make them available for workflow creation. So at the end, it's possible to create complex workflows directly from OpenAPI specifications. And this is a slide showing the just screenshot of the workflow manager, which is a tool which, as I said, is able to import OpenAPI specs and convert their operation into tasks. And then these tasks are the building blocks used to create the workflows. Workflows can then be orchestrated within applications, and I will explain later how this can work. The workflow manager is able to notify users and applications of different events at workflow or tasks level, like a failure of a task, waiting for an input, the finalization of a workflow, execution, etc. Workflows are basically a combination of tasks. It can be of two main types, system and human tasks. Human tasks are those that need human interaction to proceed, and system tasks are the ones that are automatic, without any human intervention, like calling an endpoint. Finally, just mention that the main benefit of the workflow manager is the power to upload common tasks and repetitive jobs in an automated manner, and that a big portion of that workflow configuration can be sourced directly from the OpenAPI spec, at least its initial interface. How are tasks created? So each OpenAPI spec operation is imported as one task. Each operation defines its name, operation ID, allow request parameters, and possible responses with the different attributes in each case. Once imported into the workflow manager, tasks are available to pick for workflow creation. In this slide, we can see an example of input fields mapping. The post event details endpoint of this specific API declares a body with a JSON object with different fields. Once this is imported into the workflow manager, all these body parameters will be available as input fields for the generated task. The types of these inputs will match the types declared in the OpenAPI spec and will be presented accordingly for users to configure in the workflow manager UI. For example, a boolean will be presented as a checkbox, and a string will be an input text, etc. On the other hand, response attributes declared in the OpenAPI spec are made available as potential outputs of tasks, which can then be used as input parameters of subsequent tasks in the same workflow. In this case, we can see the OpenAPI spec indicating the data and the meta attributes of the response, and for example, a field called signal request ID inside the meta attribute. So all these attributes are made available then for selection in the workflow manager controls. Workflows, as said, are configured as a combination of tasks. So in this slide, we see a very simple example, probably not a real-life one, of how tasks from different APIs can be combined together to create a workflow, and how outputs from a task can be used as inputs for the next one. So not only operations of the same API can be combined into workflows, but different APIs can be used to create and orchestrate these workflows inside your applications. As explained before, OpenAPI specs are imported into workflow manager's tasks. In this slide, we can see the different Amazon Web Services that have been used in the workflow manager application. Not all of them, but the most important ones. First of all, tasks are created from OpenAPI specs, and then they are used as building blocks for workflows. Tasks are stored in Amazon Web Services S3 as objects and segregated by buckets. So different integrations or different clients do not collide and use different buckets. Workflows, on the other hand, are stored as state machines in step functions, and their executions are represented as state machine executions themselves. Step functions is a serverless service with support for state machines, where different states are connected to each other. It supports integration with other AWS services and offers features like variable exposure or error handling, so it is possible to pass one task output to the next one. Inside the state machines, different types of states can be used. Choice states for handle conditions, map states to handle parallel executions of tasks, wait states to pause workflows for a given period of time, and others. For the workflow manager tasks themselves, task states are used with special resources pointing to a different function. These functions, which are using the Lambda service of Amazon Web Services, are then used to execute in a serverless and stateless way the different API call to third systems. Lambda supports at the moment different programming languages like Node, Python, Go, or Java, so it is great when collaborating with external teams, so they can provide their functions to be integrated within the workflow manager. Due to its stateless nature, data cannot be reused between functions and functions executions, so some form of caching mechanism is needed for this purpose. In our case, we are using Elastic Cache Redis, which integrates very well with Lambda and does support encryption out of the box, so data of private nature can also be cached. Other interesting service that we are using in the workflow manager is EventBridge and the scheduler of EventBridge, which allows a workflow manager to trigger, pause, cancel, resume, or schedule workflows using external events or in the case of schedulers, using cron expressions or other type of expressions. And Event Bridge offers the option to store rules in different event buses or in different schedule groups, so Workflow Manager can segregate very well rules for different integrations or clients, making it possible for different workflows to react to the same type of events in a different way. Finally, I just mentioned that we are using also the simple email servers, which can be used to send notifications and mails to different about different aspects related to the workflow execution. And the cool thing of all these services is that they can easily be interconnected with each other and provide great monitoring, logging, cost control, and scaling capabilities. And this makes your application visibility and transparency much better. In some cases, workflows need to be paused and wait for some time, or and wait for some human actions to take place, like review a report or verify the correctness of some generated data, or something like that. So this is very well supported by step functions via the wait for token service integration. In this case, a token is generated using a special resource called wait for task token, which can be used inside task states. State machine execution is then paused until that token is sent back to it. This type of tokens need to be stored so applications can retrieve them back when needed. In our case, we are storing them in a Postgres database, but it does not really matter. You just need to make sure that your application is able to retrieve it again. After some human interactions, which makes use of the send task success or send task failure calls, tokens then pass back to the state machine and its execution resumes. The send task calls can contain different information and metadata that is passed to the state machine together with the token. Once a workflow is created, there are several ways to trigger it or execute it. The first one is an ad hoc execution of a workflow. That is, a user triggers a workflow directly from the Workflow Manager UI or using the Workflow Manager API. Users can pass the desired parameters to be used as inputs for the workflow execution. This is useful when troubleshooting, debugging, or executing ad hoc actions like canceling workflow execution, or when using directly the Workflow Manager UI. Probably not that useful for real-life integration, since applications would need to know internal configuration of the workflows, like their IDs or similar. And this means high coupling between applications and the Workflow Manager, which is probably not the best approach when designing this type of integrations. Another way to trigger workflows is using cron expressions. So workflows can be executed on a schedule and triggered with a given frequency. As I said, this is useful when applications want to repeat same operations or execute specific actions with some desired frequency. For example, generate a report and send it to a list of consultants every first Wednesday of each month. Event Bridge Scheduler is leveraged in this case to store and manage the schedules. They are configured with special lambdas as targets in charge of triggering in a repetitive way specific state machines. Other way to trigger workflows is subscribing to events. So Workflow Manager is able to react to external events. That is, workflows can be configured to be started, paused, or resumed based on events happening outside of the Workflow Manager. This is a very powerful feature because since coordination of events happen outside of the application and standard defined events can be used to orchestrate the application, in this case, external applications do not need to know about the Workflow Manager internals, like the IDs or the specific configuration of a workflow, since the Workflow Manager will take care of everything by subscribing to the needed messages. This can be very useful in cases when users want to generate workflows in charge of storing information in a database each time a company event like dividends announcement happens. So applications publish a message indicating this situation, and Workflow Manager reacts to that by triggering the given workflow in charge of storing that data. Okay, as I already saw before, Workflow Manager allows users to import open API specs as tasks. And these tasks can be then combined into workflows to fulfill the user needs and orchestrate the workflows within applications. Okay, But on top of that, Workflow Manager provides support to combine tasks directly from the OpenAPI spec. API owners can provide configurations directly in the spec, so their tasks are directly imported as composite tasks in Workflow Manager without any manual action needed. In order to achieve that, the FactSet API program defines standard ways like links or proprietary ones like OpenAPI custom extensions, and that permits API owners to achieve the described functionality. As a first example, I'm going to show the configuration of long-running requests. Even if this pattern does not look very modern, and nowadays it is actually recommended to use event-based pattern to control long-running requests of this type, there are still many valid scenarios where long-running requests are still used, also in the API world, also in FactSet. In FactSet, the API program defines a standard for long-running requests. Basically, they are composed of 3 or 4 endpoints. First, an action endpoint in charge of the resource creation, which is an asynchronous operation that may take a long time to finish. Then a status endpoint that can be used to poll for the status and check if the creation of the resource is finalized or not. Then a result endpoint in charge of retrieving the resource creation outputs. And finally, an optional cancellation endpoint or operation in charge of canceling all the involved operations in the creation of the resource and their cleanup. This pattern can be configured directly in the OpenAPI spec using links pointing to the different endpoints of the operation. These links follow the OpenAPI standards and they are not FactSet proprietary. And as shown in the slide, the first endpoint, the creation resource 1, is configured with 3 links, which point to the respective operation: status, result, and cancellation. In this case, the FactSet Workflow Manager parses this configuration and imports, on top of the different tasks for the single paths, an extra task which takes care of the whole operation. Without going into much into implementation details, we can see that the Workflow Manager leverages a special state machine in step functions where wait states are used in order to control the polling for the status checks. Task states are used for the different endpoints, and choice states are used to decide if the result is ready and can be retrieved, or if we still need to poll for the status of the operation. So when users include this task in one of their workflows, the long-running request is handled in a transparent way, as if it would be any other asynchronous task. Other simple example of combination of tasks directly in the OpenAPI spec are list of IDs. In many cases, APIs provide endpoints to retrieve a list of IDs for specific resources. These IDs can be then used to retrieve resources using single get endpoints. Since this is a very common pattern, the FactSet API program supports a standardization for this scenario. And as shown in the slide, links can be used here as well. Workflow Manager uses this special configuration when rendering input fields which are populated using this type of lists, like combo boxes or alike, as you can see in the slide. Okay, and that's basically all. We explained in this presentation how Workflow Manager converts OpenAPI specs into tasks, and then how these tasks are used to create workflows. Finally, these workflows can be orchestrated and integrated in applications in different ways. And I also touch a bit on the different Amazon Web Services that we're using, like step function, Lambda, Event Bridge, or the scheduler capabilities of Event Bridge. But the most important thing I wanted to transmit today is the need for standardization. Following standards creates a consistent development experience in the engineering community of your company, improves API quality and the quality of all tools implemented using these APIs, and fosters team collaborations when working together. So yeah, in case you are looking for a change, please visit our careers page and nothing else. As I said yesterday, enjoy the conference again, this time in YouTube. Thanks a lot and goodbye.